I'm James Tagg from Valis Corporation. I'm going to report on an objective reduction experiment. The old sort of Copenhagen interpretation is that I look at the experiment, and the process of my looking at it gains knowledge of the experiment and it collapses. And the idea that Diosi and Penrose came up with is that this is wrong, and that actually the experiment collapses spontaneously because of an effect due to gravity or space-time. So space-time moves into two different positions, and when that space-time is moved into two positions sufficiently for enough gravity to be involved, it collapses. And so a combination of collapses then creates the thing that we feel as sort of consciousness. And so consciousness is an emergent property rather than being caused by me. It causes me to be, as it were. Here's a very simple, or maybe a complex, thought experiment. Give yourself a source of single photons and have those single photons hit a half-silvered mirror, aka beam splitter, and go to two SPADs. SPADs are single photon avalanche diodes. So those SPADs have got a 200 volts connected to them, and if a single photon appears, they will fire and conduct and actually switch quite a lot of energy. So those SPADs are then connected to two motors or solenoids, and they move those motors. And the question is, do the motors move in superposition, or does only one motor ever move? So do you get immediate collapse, or does collapse take some time? If collapse takes some time, then you'll get double slit interference because both motors will open, and then shortly thereafter they will collapse back to a single motor opening, and you get single slit diffraction, and that will be the result of the experiment. We actually use a Mach-Zehnder mechanism to do this because the motors and shutters would simply weigh too much. So again, it's very simple. We have our single photon generated, two SPADs, and they move mirrors. We build our own mirrors, and our own mirrors are made out of a combination of piezo material and wired up with copper tape and conductive adhesive and so on. And so we can generate a very lightweight moving mirror. Put that all together with a source of single photons, which we generate in a refrigerator to keep the dark count down, and we have our experiment. Now, the interesting thing, or a couple of interesting things about the way the experiment works. The first is most experiments that put things in superposition take two very small objects and move them completely apart. We actually take two relatively large objects, our mirrors, and we move them a very small distance apart, an angstrom or 10 angstroms or so. Because the distance moved is squared, then that means we get a very tiny factor into the equation, and then therefore that gives us a very long time. So we're talking about times in the range of 1 microsecond, which if you're talking about superposition is ridiculously long. The other thing that we have a big problem with, of course, is decoherence. Now, decoherence is this feature that if I try and put two things, try and put a mirror into superposition, it will be buffeted by air molecules and all sorts of things, and eventually it will spread out the quantum information and it will just become a complete mush. But the interesting thing about this complete mush is it's still symmetrical. So if you look at the density matrix before it decoheres, it's symmetrical or very nearly symmetrical, and it has these phase terms. And once it's decohered, it's actually even more symmetrical, right? It tends to zero. So you have a half, zero, zero, half, completely symmetrical. What we actually need is an asymmetrical collapse. We need it to collapse to one or other thing. So 1, 0, 0, 0 or 0, 0, 1. That's what we need for collapse. And so our experiment, because it's symmetrical, manages, we believe, to separate collapse and decoherence, and therefore you can do it at room temperature. There is some previous experience of quantum experiments that have this sort of strange feature, one that everyone refers to as the Cheshire Cat, where you can measure the location of the photon and the polarization of the photon independently. So you can actually say that the cat went in one direction and its smile, its polarization, went in a completely different direction. Extremely weird. So having those weird effects is not outlandish. We already have outlandish experiments out there that do things. So our result is that we do get a departure between the control and the experiment. The control we do by simply turning the laser off. Now there is no source of single photons, there's just doubt count. So there can be no superposition, so all of the firings are uncorrelated. When we have correlated firings, we then get a more pronounced effect. Blowing it up and actually looking at sort of the detail with the error bars that we get in our experiment, we can see that actually it's a significant departure between the two. And that departure, unfortunately, there's a ring to it that we have on the top of it because the mirrors have mass and they vibrate and so on. But we do get a departure between the two, and then they come back together again, and then we don't get a statistically significant difference past about 1.5 microseconds, which is the calculation that you get from the how Penrose-Fuentes paper about the amount of superposition time we'd expect for a mirror of this weight separated by this mass. So that was a positive result, which we got about a year ago. That's a fairly dramatic result to get, and we've been working on improving the quality of the experiment for a year. We've also been building a completely different way of doing the same experiment in radio frequency. So in this instance, we have a diode laser, we have two single photon avalanche diodes, and now we use those to switch on two RF FET switches, which then detect the output of a signal generator in superposition. Normally what we would get is that we get the left channel fires, we get the right channel fires, and after both channels are fired, we are detecting with both antennas, and therefore we're getting constructive interference, and therefore getting a stronger signal. And until we do that, then we just get a lower signal. So we get a lower signal, and then when both of the switches are switched on, we get a higher signal. But we also sometimes get a situation where we clearly got the normal detection, left channel triggered and right channel triggered, but we actually fire effectively both sides simultaneously. And that we think is a constructive interference or a superposition detection, but in the RF domain rather than with mirrors and photons. So I'll show you a little bit of the experiment now just to give you a quick tour around it. So here is our experiment, and you can see that it's detecting photons. So we trigger off, actually we have to do a quantum eraser, so we link our two photon detectors together so we can't tell which way it went, otherwise of course which way information you have to count the mass of my brain into the calculation. So we get a first photon, or the left gate fires and then the right gate fires. So the first photon fires this one, and then the next photon that turns up that ends up going the other way fires the second gate. And we get, then we're picking up, so we get a combination here where we pick up the first gate fires and the second gate fires. Now you can see that sometimes it goes straight up, and this is we're arguing that is the superposed detection. Now some of those superposed detections are wrong, so there's one where it happened very quickly, but that's because we had two photons arrive very, very quickly. But if we keep going, we will get an example where we had a first photon and a second photon turned up, but actually we got detection in superposition. We have a couple of positive preliminary results. It's quite interesting. Thank you for your attention.